Today, we're going to crack the code on a real GCSE chemistry exam question. We're not just looking for the right answer. We're going to build the perfect answer, the exact one that examiners are trained to look for. Think of this as getting a VIP pass right into an examiner's mind. Okay, let's dive in. You know, the secret to getting top marks isn't just about knowing your chemistry. It's about speaking the examiner's language. By digging into the official mark scheme, we're getting a direct look, word for word, at the exact phrases and scientific keywords that score points. So here's the setup, taken straight from question 4 of an AQA paper. We've got paper chromatography in action. An orange dye is put on the starting line. In experiment 1, the solvent is water. In experiment 2, it's ethanol. As you can see, that orange dye splits into yellow and red spots, and they travel different distances in each experiment. Our job is to figure out precisely why. First up, we're testing our basic understanding of chromatography. It's like a scientific puzzle. Why do these dyes behave so differently when everything else seems pretty much the same? Let's break down the science. Okay, let's zoom in on experiment 1, the one that uses water. You can see it clear as day. The yellow dye has raced way ahead of the red dye. The question is, scientifically, what's the reason for this? What's the actual chemistry that's causing this separation? And here is the perfect 2-mark answer. Mark number 1 is for the simple observation. Just state that the yellow dye travels further. But the second, and really crucial mark, comes from the explanation. It has a weaker attraction to the paper. Remember, in chromatography, the paper is the stationary phase. It's not going anywhere. The less a substance sticks to it, the further it gets carried by the mobile phase, in this case, the water. So the key is linking distance to attraction. On to the next clue. We're still tracking that yellow dye, but this time we're comparing its final position in water versus its position in ethanol. And wow, there's a big difference. So why? Let's check the mark scheme and see how to build this answer.
This is a 3-marker, and each point is laid out just perfectly. First, state what you see. The dye travels further in experiment 2. Second, identify the one thing that changed. The solvents are different. And third, hit them with the scientific principle. The yellow dye is more soluble in ethanol. Since the solvent is the mobile phase, higher solubility means it gets carried way further up the paper. Simple as that.
Excellent. So the investigation is shifting gears now. We're moving from explaining the why to interpretation and calculation, 2 skills that are absolutely critical for any scientist. And we're about to meet a new character in this story, dye B.
Here's the visual evidence side by side. On the left, we've got our original orange dye, dye A, which clearly split into 2 spots. Then on the right, a new experiment with dye B. Notice the difference? Dye B leaves only one single spot. This image right here perfectly illustrates the whole concept of purity in chromatography. The exam wants us to compare the purity of these 2 dyes, and then justify it with evidence from the chromatograms. So what's the verdict? And how do you phrase it to make sure you get full marks? Let's find out. Now, this is where the precision of your language is so important. To get the marks, you have to state that dye A is impure or a mixture, while dye B is pure. And the reason? Well, A produces 2 spots, which means it's made of at least 2 different things, while B produces only 1 spot, indicating it's a single substance. It's a simple, powerful rule. In chromatography, 1 spot means pure, multiple spots mean it's a mixture. All right, time to bring in the math. We're given the RF value for that pure dye. It's 0.48. We're also told the dye itself moved 5.4 centimeters. The task is to calculate how far the solvent front traveled. This is a classic test of rearranging an equation, so let's see how the marks are awarded for this one. And here's how you lock in all 3 marks. Mark number 1 is for correctly rearranging the RF formula. Mark 2 is for substituting the values in the right place, 5.4 divided by 0.48. And that final 3rd mark is for the correct answer, 11.25 centimeters. Showing your work here is absolutely essential. It's how you prove you know what you're doing. We are not quite done with the RF value. The next question really digs into our deeper conceptual understanding of what this number actually represents. It's a real test of whether we've grasped the core principles. Now, this is a great question. If you let the experiment run for longer and the solvent travels, say, twice as far, the RF value stays exactly the same. It kind of feels like it should change, but it doesn't. Why is that? The mark scheme's answer here is just beautifully simple. The RF value is a ratio. It's the proportion of the distance the spot moved compared to the total distance the solvent moved. And that ratio is a constant property for a specific dye in a specific solvent. So it doesn't matter if the solvent travels 5 centimeters or 15 centimeters, the dye spot will always travel the exact same proportional distance. It's like its chemical signature. For the final part of our question, we're asked to zoom out from the school lab and think about how this kind of analysis is done in the real world, with some pretty advanced instrumental methods. Paper chromatography is simple and visual, but what are the benefits of using a sophisticated machine like a gas chromatographer instead? The question asks for any 2 advantages. Let's see what the examiners will accept. And here are all the possible correct answers. You only need to give 2, but look at the keywords. Sensitive, meaning it can detect incredibly tiny amounts. Accurate, so the results are more precise. And faster, which is a huge advantage in any professional lab. You could also say it can use a smaller sample or provides greater resolution, which just means it's better at separating very similar chemicals. Any 2 of these will get you the marks. So there you have it. We've just dissected a 13-mark question, guided entirely by the examiner's own mark scheme. The big takeaway here? Precision in your language, showing your work, and truly understanding the why behind the science. That's what separates a good answer from a perfect one. It's not just about passing an exam, it's about learning to think like a scientist.